So, bom dia, tudo bem? So, it's a pleasure to be back in Brazil, and thank you for coming to the first talk right after the banquet. I know it's always a liability, so I'll try not to make you go to sleep very fast. So, I'm going to tell you here a story about how to get Higgsino dark matter in an extra-dimensional model, which for me was like going back 20 years back in time, because some of the calculations that I did for this paper, I already did for my PhD thesis. So this is work done with my fellow Notre Dame professor Adam and Mariano Quiroz, who happens to be here and happens to be my PhD advisor. So I'll introduce the model, and then I'll show you what constraints you get when you impose electroweak symmetry breaking and a Higgs whose mass is 125. But before that, it doesn't change slides.
No?
No.
Okay, so just use the laptop for now. I'm going to change the better.
Okay. So I want to pay some tribute to Eduardo. Unfortunately, I won't be able to be here on Monday. And Eduardo was a very good colleague, a very good physicist, but best of all, a very good friend. I met Eduardo I think in the year 2000 in a workshop in Argonne. And since the very first moment we clicked, we were very good friends. We share common interests, we share common controversies about Spain and Colombia and the conquest and things like that. And I suffer a lot while he was suffering. And it's too bad that someone of her talent actually leave.
I know why it's not working.
Because you, I know why, yes. Where is it? No, here. Yes, it wasn't connected. Yes. So yes, I want to dedicate this talk to my good friend, Eduardo. So, as introduction, we have seen this several times. This is the cosmic pi. So when you take into account several measurements, mostly the cosmic microwave background, this is the energy budget of the universe today. 70-some% of it is dark energy. I have nothing to say about dark energy because most people in this room, I think they have very little to say about dark energy. 24% is dark matter. We know it behaves like matter. And then this is us. So dark matter may be the most established reason for physics beyond the standard model. Dark matter is something that cannot be accommodated in the standard model. We don't have an stable neutral particle that could explain this abundance. And even models of primordial black holes, you need to modify the Lagrangian of the standard model to include new degrees of freedom to be able to produce those primordial black holes. So from the experimental point of view, I think this is the most established reason to go beyond the standard model. The rest of them can be accommodated by hand waving. The hierarchy problem, well, no one told us that the Higgs has to be natural. Inflation, well, you can solve the horizon and the flatness problem by boundary conditions, and in the same way, you can explain baryogenesis just by boundary conditions. But as far as I know, there is no way to explain the dark matter abundance without introducing a new degree of freedom.
Well, neutrinos.
What?
Neutrino masses.
For me, neutrino masses are a standard model. You just do this. That's, for me, neutrino masses. It's a new degree of freedom, but it's a Dirac mass. Majorana masses, I agree with you. But if neutrinos are Dirac, for me, maybe you can call it beyond the standard model Manon-Tropo. Yes. But of course, I didn't tell you why the Yukawa couplings are like that. Flavor is also not explained. So for that matter, one of the biggest, well, not biggest, but maybe one of the most studied solution is a thermal relic. We have had several talks and an excellent colloquium by Alejandro explaining why this is a very good solution. And the reason is in this plot is that the thermal abundance of a particle that was on thermal equilibrium with the plasma is very much independent on what happens very far in time. It just depends on infrared sensitive quantities, which is the cross-section of annihilation and the velocity. So you don't depend on details of cosmology. You just assume that depending on the value of the annihilation cross-section, you can get the relic abundance just by a thermal process. So all of dark matter is encoded in just infrared particle physics behavior. It's very elegant, and it doesn't depend on what happens very far in time. So we all know that for a WIMP, a weak interacting massive particle, whose mass is close to the electroweak scale, and which couples with weak couplings, then you can reproduce the measured relic abundance, just assuming that m, the mass of this object, is between 100 and 1 TeV, and that the coupling is weak, in the sense of SU2 weak. And of course, we all know this has interesting consequences, because if what said this is the early universe annihilation, so you have normal matter, you have dark matter, they are, in principle, for last temperatures, they are in equilibrium. Freeze out works that when you go below the temperature where you can produce a pair of dark matter particles, then this interaction is not possible to go in this direction. It's possible to go in this direction, so if the universe weren't expanding, then we will deplete all of dark matter, but because the universe is expanding, then at the end of the day, there is a competition between these two particles meeting each other and producing standard model particles, and the expansion of the universe that is going to make these two particles never meet. So this is how freeze out occurs, but of course, if you interpret this as a Feynman diagram, then depending how you see it, you can get direct detection of dark matter, which is dark matter interacting with us, maybe a nucleus in like xenon, and then you see the recoil of the nucleus. Then here is indirect detection again, so two dark matter particles, they may annihilate, especially in the halo, and then they produce normal matter, and of course collider production is in this direction. There are caveats for this process. One shouldn't take this process to be the same process always, especially if you're in a situation where you have a funnel or resonant annihilation. Well, you have to take into account that there could be cases where direct detection is suppressed, whereas indirect is not, and so on and so forth. But in general, this picture is very elegant. On the other hand, even though I said there is no reason for the standard model to be natural, the hierarchy problem has guided lots of us to study possibilities to explain why the Higgs is natural, and one of them is supersymmetry. And of course, supersymmetry and dark matter are ideas that you can merge them very well, and indeed in the MSSM, you have several possible candidates for dark matter. You have, for example, this neutrino, but this neutrino turned out to be not a very good dark matter candidate because its annihilation cross-section is too large. If you are in gauge mediation, the gravitino could be the lightest supersymmetric particle, but the interaction of the gravitino are non-renormalizable, and there are some issues, and I'm not going to talk about that. Or the possibility that most people consider is that the LSP is a neutralino. Neutralinos are admixtures of gauginos and Higgsinos, and depending on the nature of those, then you can have for different ranges of masses, you can reproduce the relic abundance. For 100% Beano, you most of the times overclose the universe unless you're in a resonant situation. You have to have coannihilation with squarks, leptons, and so on. And then you can well temper, that is, you can have a non-trivial mixture of Beano-Higgsino or Beano-Wino. But it is true that in most of the regions of the parameter space, direct detection rules out, unless you are in one of the blind spots that Carl Locke talked about on Wednesday. For pure states, Higgsino of around 1.1 and 1.2, it can reproduce the relic abundance, and so far is okay with respect to direct detection. The other pure state is the Wino. The Wino has to be around 2 TeV to reproduce the relic abundance, and there is some controversy if that's ruled out or not because of indirect detection. The reason is that the Wino has a very big Sommerfeld enhancement, whereas the Higgsino doesn't. I'm not going to talk about the Wino in this case, and offline we can discuss what are my views on that. So in this talk, I'm going to build a model that has just 3 free parameters, and I'm going to fix these 3 parameters requiring these 3 conditions. I'm going to demand that I want to have the correlated abundance with a mostly pure Higgsino. This essentially fixes some scale. The Higgsino is going to be between 1.1 and 1.2 TeV. And then I want to have correct electroweak symmetry breaking. That is, the BEF of the Higgs is 174 in the usual normalization of susy. And also, I want to have the correct Higgs mass, 125. And of course, I want to be in agreement with all experimental bounds. So what is the model? Well, let's go back 20 years, as I said, and I'm going to resurrect 5 dimensions to you. I'm going to build this in a 5-dimensional model. This X dimension is going to be flat. This is not a Randall-Sundrum situation. This is a flat X dimension. Of course, you can view this as an EFT whose cutoff is 20 TeV, and you can ask me, okay, why are you paying so much attention? Well, since I suppose this theory is supersymmetric, wherever theory UV completes, this effective theory is going to be supersymmetric. So anything which is only sensitive to infrared physics, it would be not very sensitive to the UV completion of my theory. So I'm going to assume that you have an X dimension whose size is pi r, and I'm going to compactify in an orbifold S1 over Z2. That's a fancy way to say I'm compactifying on an interval. Why am I compactifying on an interval and not on a circle? Well, for those of you who know X dimension, this is obvious. In 5 dimensions, there is no chirality. The minimal fermionic dimension is 4, which is the same as the Dirac fermion. On the other hand, we know the standard model is chiral. So then we have to compactify in a clever way to create chirality, and this is the role of this Z2, which is going to act like a parity. By the same reason, the minimal supersymmetric contact in 5 dimensions is equivalent to what is n equals to 2 in 4 dimensions. So this is a non-chiral theory. The only interactions that you can have in n equals to 2, if you don't do anything fancy with the Kähler, that I'm not going to do, is gauge interactions or a mass. So then the role of Z2 is that it breaks half of the supersymmetries. So you have to make some fields to be even, and automatically other fields are going to be odd. This is also the same thing you do in Randall-Sundrum. These things is very well known, is how you compactify in an interval. If you want to see these in Fourier series, then what you're doing is that compactifying in these, you're going to have functions that you have expansion in cosines and functions that have expansions in sines. So this is a cartoon of what I'm going to do. I'm going to have an interval, I'm going to have 2 branes, and as opposed to what I did in my PhD thesis, in this model, everything is in the bulk. Everybody and his brother is in the bulk. Nothing is localized, or no fields are localized on the branes. So every field of the standard model has KK modes. So all fields live in the bulk and form n equals to 2 representations, as they should. And of course, you are going to decompose these fields in KK modes, and the derivative with respect to y, or the derivative with respect to x5, will give you masses, okay? So the theory in the bulk has an SU2R symmetry. In the same way that n equals to n equals to 1, d equal to 4, the normal supersymmetry 4 dimension, you have an U1R symmetry. It's a symmetry, it's an U1 that theta, which is the generator of supersymmetry, if you multiply by a phase, nothing changes. Well, in n equals to 2, what you have is an SU2. You can view this in super fields or in super space, that you have two thetas, theta 1, theta 2, and there is an SU2R symmetry that rotate among them. Global. This is global. Actually, when you gauge it in supergravity, there are two different ways of gauging, of doing supergravity. You have ungauge supergravity and gauge supergravity, but that is irrelevant to what I'm doing. Everything is global here. So this symmetry, this SU2R, makes Higgsino transform, which is the same that what happens in n equals to 1. A Higgsino masses breaks the R symmetry, for example. And also scalars in hypermultiplets also transform non-trivially with respect to this SU2R. On top of that, like in the MSSM, we have to add 2 Higgs hypermultiplets. Hypermultiplets are the same as chiral multiplets, but in n equals to 2 notation. So I have to include 2 of these hypermultiplets for the same reason that you have to include 2 Higgs chiral multiplets in the MSSM. Even that you think that you could put them on the same hypermultiplet, because of the way this is constructed, you cannot embed both Higgses of the MSSM in the same hypermultiplet. Since you have 2 hypermultiplets, there is a global SU2 that transforms these 2 objects, and this is what I would call SU2H. It's also a global SU2. So why am I introducing this global symmetry? Because by relating the boundary conditions in both endpoints via this transformation, which is a symmetry of the theory, it's a global symmetry of the theory, what I'm doing is that I'm creating twisted boundary conditions. In normal, if I didn't do that, then if I demand a field to be even on one endpoint of my interval, then it will be even on the other endpoint. And the same would be with the odd. By introducing this twist, for some fields, what I'm effectively doing is removing the zero mode, because if I'm twisting the boundary conditions, then you cannot have a flat mode. This is another way of doing what Scherk and Schwartz introduced at the late 70s as the Scherk-Schwartz breaking, Scherk-Schwartz susy breaking by compactification. So in a sense, what I'm just doing is that twisting the boundary conditions in both endpoints. This is something that is done every day that you do compactification in string theory. So these twists, since they are just phases, are going to be related to 2 numbers, QR and QH. So QR relates the twist with respect to SU2R, and QH relates to the twist with respect to SU2H. In truth, even though I have SU2R and SU2H, because of the orbifold, I'm breaking SU2R to U1R and SU2H to U1H. And then these QR and QH are the phases related to those U1s. So all of this lets me decompose every field in the bulk in the following way. So if I start with gauge multiplets, a gauge multiplet in 5 dimensions has a vector boson who has 5 components of shell, 2 Higgsini, and a real scalar, as opposed to in 4 dimensions that you will have 4 components here, the same 2 Higgsini, and a complex scalar. What happens is that at the end, V5 acts as the imaginary part of the scalar. So then, with parity, I decompose it in this way. Of course, I want the gauge boson to be even, because I want gauge bosons. So then one of the Higginos are going to be even, and then the other, which is a chiral multiplet, will be odd. This is without the twist. With the twist, since gauge bosons don't see the twist, Well, they're going to be just a tower that goes like n over r, and n equals to 0 is going to be the gauge boson that we know. The Higgsini, they don't have a 0 mode, as you can see here, but they get a KK mode which goes like QR plus or minus n over r. And then this poor guy is left alone because V5 is eaten by the gauge boson, and then you're left with a real scalar whose mass is also n over r without a 0 mode. It doesn't have a 0 mode because it's odd. So in this way, at the level of the 0 modes, I recover the standard model, just the gauge bosons. Those are the only ones that have 0 modes. With hypermultiplet, it depends. For matter is similar than for Higgsinios. For vector multiplet, sorry. So you have a hypermultiplet that you can view as two chiral multiplets, one left-handed, one right-handed, to be vector-like. And then one of them is going to be even, and the other one is going to be odd. In this situation, I decide the left to be even, but you can be the opposite. By doing the same SU2R twist boundary conditions, what I have in this case is that you have a set of chiral fermions whose mass is n over r. They are the Dirac component with this one. The 0 mode is chiral. Only in this case, QL0 exists. There is no QR0. But the quarks are massive. And as you can see, they have the same mass as the Higgsino, at least at 3 level. So again, in this construction, I recover as 0 mode only the chiral fermions and nothing else. The Higgses are different because if you try to do the same thing with the Higgses, you get what you don't want. Because what you want for the Higgses is a massless scalar and massive Higgsinos. That's not what you want. That's why for the Higgsinos, or for the Higgs in general, you introduce both twists. You have a twist with respect to SU2H and a twist with respect to SU2R. So you decompose both Higgses that are hypermultiplets into two chiral multiplets. SU2R relates them here, and SU2H is a rotation here. So then, when all fog clears, you have the following spectrum. For the Higgsinos, they don't have a 0 mode, and their mass is dominated by QH. QH, in a sense, is like the mu term in the MSSM. QH doesn't break SUSY. If QR is 0, then all what you're doing is that you have given a common QH for everybody. QH doesn't break SUSY in the same way that mu doesn't break SUSY. But QH is there in the same reason that mu is there. Without QH, you don't break electroweak. But then, since the Higgses also get a piece by QR because they are scalars, then you get one that goes like QR minus QH plus or minus n, and one by QR plus QH plus or minus n. So if you want a massless Higgs, well, you just say QR is equal to QH, and here you have a massless Higgs. We are not gonna assume that a priori because we want QR and QH to be independent so as you get the correct electroweak break. So again, by these two twists, at the level of 0 modes, you just have the standard model. Just the standard model. And then above that, at QR over H, you have the supersymmetric parters, and then at 1 over R, which is higher, is when you start having KK modes. Okay? Of course, this is very good, but I haven't included Yukawa interactions. Yukawa interactions cannot exist in the bulk because it's n equals to 2. What you do that is that you write them on one of the branes. If you want to start playing with flavor, and that's I can answer about neutrinos, well, you can think about localizing different Yukawas in different positions of the orbifold. We didn't do that. We just include the usual superpotential in one of the branes. This is needed in order to give masses to the chiral fermions. Okay, so what are we going to do? We're going to identify our physical Higgs with the Higgs whose mass is QR minus QH divided by R. We want to make sure that the second Higgs is very massive, and that will allow us to be in the alignment limit. Why do we want to be in the alignment limit? Because the measurements from the LHC tells you that the 125 Higgs is at least 90% standard model Higgs. The alignment limit tells you that the Higgs is 100% standard model. So by making sure the second Higgs is very heavy, it won't get a BEF. There is a periodicity condition, so we're going to assume that QR and QH are always less than a half in order not to overcount the number of solutions. So how are we going to fix the parameters? QH is very easy. The Higgsino is QH divided by R. Well, since I want the Higgsino to be between 1.1 and 1.2 TeV, that automatically fixes QH.
You have fixed R already?
No, I haven't. This just fixes QH divided by R. You're absolutely right, yes. This is because I want. I didn't have to do this. But this allows me to explain the Darmstadt abundance. Then now I have two free parameters, QR and R, and two conditions, electroweak symmetry breaking and Higgses. So yes, I'm not predicting any of these, I'm just describing. But I have three free parameters, I impose three conditions. So this is trivial, let's work on these ones. So in order to impose these two conditions, I have to calculate the Higgs potential. This is the Higgs potential, tree level, this is this, and this is 0. There is no quartic at tree level. You can view this as being at tangent beta equal to 1, but don't go too much into tangent beta because it's not the right language. You can also view that this is a consequence of n equals to 2. So tree level, you haven't broken anything. You just have a positive potential. But of course, you have to include one loop corrections to this and to this. This one loop correction comes from all the particles that we have. And this is taken, by the way, from my PhD thesis, which is amazing. So I go back to my PhD thesis. I calculate the corrections to the Higgs mass from gauge interactions. You have the gauge boson, the Higgsino, the scalar components, or the I don't know how some people call it this, the R scalar, because it's related by R symmetry, and then some interaction, and this was shown in Mirabelli-Peskin in a paper in the 1998, that because of supersymmetry, there are some extra interaction. You get this, and the correction to the Higgs mass is proportional to G squared and Gy squared, and these functions, which are just polylogs. These corrections are finite, they're UV finite and infrared finite, and as usual, they're positive. This is nothing new. We know that gauge interactions tend to give a positive correction to the Higgs. You have also corrections coming from the Yukawa. These are brane interactions, so that's why the form is different. Here you are summing over the whole tower, whereas here you have not summing, the sum is outside because this interaction is a bulk. Here, a coherent sum of all the squares is there, that's why the form is the same. Don't pay too much attention to the I because there's a Hermitian conjugate there. So you calculate it, now it can be negative depending on the values, and there is a small dependence here, is UV insensitive, and it has a dependence on the value of the matching scale. And then you have also the correction to the quartic. These are the diagrams. These are similar diagrams that you get in the MSSM, for example, quarks, whatever. And you can write this in a very compact way, which is, if you look this, is just the sum of the propagator of the bosons minus the sum of the propagators of the fermions. And then you integrate of the momentum. And this is the brain-to-brain propagator in Euclidean space, because we have already gone to the Euclidean in this model. I don't give you the analytical formula because the analytical formula is horrible. Mathematica doesn't like it to do it. It's, again, also ultraviolet finite, but it's going to be infrared divergent. Why is infrared divergent? Well, the infrared divergence, it comes from here because I haven't broken electroweak symmetry, so you have a massless stop there. Okay? So the contributions, all contributions to the mass are finite. Why? Because I'm regulating summing over all KK modes. This is very well known since the time of my PhD thesis. Everything is finite. The quartic coupling has an infrared divergence related to the top quark. So that is just telling you that you have to run and you have to match. So we're going to perform the matching with respect to the standard model at the mass of the squares, which is QR over R. So you're going to run the standard model to Q over R, and then you're going to match here. Of course, you can discuss where are you matching here and not at a half of this or twice. Yes, I know. But this is the usual theoretical error in my calculation. And I have two conditions, one on the masses to get the correct electroweak symmetry breaking, and one on the quartic to get the right 125. 125 is going to be essentially lambda times V, and the mass fixes V. So here I plot in this QR over R, which is the T-level masses of the particles with respect to QR. So this is the condition for an electroweak symmetry breaking for a Higgsino of 1.1 to 1.2 TeV. This is another solution, but in this case, the Higgsino is not the LSP. The Higgsino is the highest particle in your spectrum, so we should focus on this one.
What is the LSP in the other case?
The LSP, we calculated, and it tends to be the style. So, no, not a good. The Gravitino gets the same mass as every other QR over R. So the style gets a small negative corrections. Yeah. But also you are ruled out because the gluinos are 1 TeV, forget about cosmology. The problem here is not the cosmology. So this is the line where the Higgs is 125. And in this small area, you are not in the alignment limit. So forget about this. So the solution we want is here. So at least for once, it's surprising that you have a consistent solution. It could have been that these two lines would cross in a place where this was completely stupid. So they cross around 2 TeV, but so then when you include one loop corrections, then these are the two ends of this band. So QR and QH has this value. 1 over R is quite big, so no chance of getting Kecky modes at the LHC. These are the 3 level values of everybody except the Higgsinos. Remember, I'm fixing this. And then the mass of the gluino, once you do the small running and go to the pole masses, is between 2 and 2.1 TeV. So you are borderline. I'm going to show you the bounds. And then the second Higgs is very heavy. Okay? So then, what are the experimental constraints? The biggest experimental constraint comes from the gluino. The CMS and Atlas in the same way, they produce the plots depending if the gluino decays 100% to the tops, to the stops, 100% to bottoms, or 100% to the light flavors, to the 4 light flavors. If I look just to this, I'm not ruled out because if you put 1.1, 1.2, the bound is 1.8, 1.7. Of course, that's not the whole story because our gluino can decay, depending on the range of masses, to 5, 5.5, or 6 flavors. So you have to combine the stops, one decays to tops, one decays to bottoms, and one decays to the light flavors. We need a naive estimate, and the bound right now is 1.9 TeV. But of course, is in the verge of being either ruled out or discovered, depending if you are Carlos or someone more realistic. If you are Carlos, he will tell you that we are about to discover the gluino. And then the other experimental constraints is on the Higgsino, direct detection, since this is the cross-section as a function of the fraction of Higgsino. Our Higgsino is 99%, our neutralino is 99% Higgsino, so the cross-section is 10 to the minus 10, so Xenon 1T hasn't ruled out, Xenon NT is supposed to come down. And also these values are also borderline with indirect detection, okay? So
in the previous plot, the fraction is close to 1, but if it's not 1, what is the other component of the neutralino?
Bino is that you just have to diagonalize the matrix. You have the usual matrix as in the MSSM, so you have M1 and M2 are 1.9 TeV, mu is 1.1, so you diagonalize.
But I was surprised so if you go, for example, to 0.9, you have a prediction for the cross-section, but that should depend if the other 10% is win or
I didn't. I just took this from this paper, so
Maybe there's some assumption.
maybe you're right. Maybe here they are assuming that it's Vino Higgsino. Yes. But in this case, in our case, I calculated the cross-section was 10 to the minus 10. So a 2 TeV gluino may need, we don't know in this case, since it decays a lot to light jets, you may get high Lumi. The first chances to discover this Higgsino, that's also a paper by Adam and Bramante and other people, at 1.1, 1.2 TeV, you need xenon NT or LZ because even in the CPP or in the next Hadron Collider, at 1.1, 1.2 Higgsino, the cross-section is very, very low. And then one of the, I don't know, amusing part is that the fine-tuning in this model is smaller than normal. Why? One is because it's low, this is low supersymmetry breaking. Any theory with low supersymmetry breaking has less fine-tuning. But also, it has a smaller fine-tuning because the electroweak scale here depends linearly and not quadratically on the parameters. Electroweak breaking here goes like QR minus QH square, as opposed to in MSSM that goes like MH up square minus mu square. So here we're tuning things linearly, whereas in MSSM you tune things quadratically. Don't spend too much time thinking of this because this structure is going to be violated via one loop. So this is very similar to the no-scale model in a sense. So my conclusions before Farinaldo starts throwing tomatoes on me is that I have gone back to my PhD thesis 20 years ago, and I have built a 5-dimensional supersymmetric model with shared source supersymmetry breaking. This is breaking via boundary conditions. I have 3 free parameters, QR, QH, and R, and they are fixed by assuming the right relic abundance. I'm sorry Carlos is not here, but that's the reason why the Higgsino dark matter is much better than anything else. Then you have the right electroweak symmetry breaking and the Higgs mass. And at least it's extraordinary that a model with so few parameters, it can be fixed by these conditions and the spectrum is not ruled out. So then one have consistent solutions. The LSP is just by our election is 1.1, 1.2 TeV. And then the mass of the gluino has to be above 2 TeV, which is right above the current experimental bound. So this experiment, this spectrum can be proved, especially the gluino, in high Lumi. The squarks, when I gave this talk in front of Michelangelo, he did a fast calculation, and he thought that a 1.9 squark is impossible even at high Lumi because of the cross-section. The cross-section is too low. And the Higgsino, you need the next generation of direct detection. Okay, obrigado.
Questions, comments?
So how your R is the size of the extra dimension, right? So you fix it phenomenologically, but ideally you want to know.
There are ways to dynamically generate this radius. Actually, Mariano worked using Casimir energies and things like that. But yes, you're right.
Don't you introduce new parameters when you?
Well, but normally those degrees of freedom are massive. Extra matter.
Extra matter. And
So you have to introduce extra matter. Either you use Casimir or use Goldberger-Weiss. Yes, you have to use an extra degrees of freedom, but those extra degrees of freedom are also end up having masses also at the same level, like 1/R. So I don't expect those to affect any phenomenology. And on top of that, normally they are singlets. They're just scalars, something like that.
So you use the 5D because then you get parameters.
Well, we use 5D because you use the Scherk-Schwarz.
Yeah.
Yes, and also because with one 5D you have this thing that the sum over all modes is finite. If you go beyond 1x dimensions, the sums are no longer finite. You have dependence on the cutoff.
But then how would you know at the LHC if it is this model? I mean,
at the LHC is impossible.
It's impossible
because the KK modes start at 5 TeV. So you need to go to to a collider, a 100 TeV collider, something like that, to start being the resonances. At the LHC, you will never see that.
Okay.
What happened with the squarks in the model?
The squarks are 1.9 TeV.
And they affect the correction to the Higgs mass?
Of course, yes. When I have calculated here you have the squarks and the quarks. Yes, yes, all of them.
So for the 1 TeV Higgsino, you can still play with quantum relations or something to really suppress the direct detection. I mean, yeah, you can, right? So even with the next generation of dark matter experiments, you can still go below there.
If you yes, you can play
play.
around if you want. And of course, if this model is ruled out as it is, then by pushing everything up, you will be okay with the experimental constraint. Then the issue is, okay, then you are overproducing. But then you can start playing with cosmology and things like that.
Further questions? No? So let's thank the speaker again. And we go for coffee break.
Now you can have your breakfast. I said it in the first that you happen to be my advisor. And I think... By the way, yes.
Did he pass the time?
Mariano is my PhD advisor for those that hadn't noticed.